Happy New Year, and also very welcome to join our New Year Festival webinars. So first of all, today is the 5th day of the Spring Festivals. So today is the day for riches. Of course, we are wishing for publications. And here is best wishes for the new year. And also, first of all, I would like to introduce our CGCA. CGCA is a non-profit organization which is registered in Cologne, and we are aiming to bridge between China and Germany, of course, between European countries, and communication between researchers, scientists, and students, of course, and companies. And we also organize different events. For instance, our annual events has a very long history, and also organize and host this junior scientist program, junior science prize. And this is just example to show how we prize the great scientists in Germany. And we also have the Chunhui program, which is a collaboration with the Chinese government and support scientists travel back to China and present their results and building connections. And of course, as Chinese organizations in Germany, we are the representative of the Chinese chemists. So this is just an example to show there are discriminations happened in the former time, and we also communicated by the later to the Angewandte Chemie. Yeah, and of course, we are very welcome to join our CGCA. And this is the protocol how you can join our CGCAs. So just a short introductions. And today we have 4 speakers today for our biochemistry session. First is Dr. Yingke Wu, and he will talk about the symptom of cells. And the second is Xinjian from EPFL Lausanne. And the third one is Professor Yuxuan. He already got professorship in the Sichuan University of Science and Technology. And the last one is me. So welcome to our events. And first, I would like to introduce Dr. Yingke Wu. He is now the group leader in the Max Planck Institute of Polymer Research in Mainz of Germany. And he's received his master's degree from Sichuan University in Polymer Science and Engineering. And in 2017, he moved to Germany and joined the Max Planck Institute of Polymer Research. And after that, he got his PhD grades in 2021. And now in 2023, he received and was appointed as a group leader in the Max Planck Institute of Polymer Research. And today he will give us a talk about the symptoms of cells, detection and beyond. So welcome, and the stage is yours, Dr. Wu.
Yeah. Thank you very much, Su-Yuan, for the nice introduction. I think now. Yeah. Can you see my screen now?
Yes.
Yeah, great. Yeah. Yeah. Good afternoon, good evening, everyone. Today is my pleasure to give the talk in CGCA webinar. I wish everyone a happy Chinese New Year. And today I would like to introduce you our current work in my subgroup. We mainly focus on detecting the symptoms of cell and manipulate. So my name is Yingke Wu. Yeah, okay. And I guess everyone is very familiar with the coronavirus nowadays, and luckily it had gone. And once the people was infected by the coronavirus, they usually showed a lot of different symptoms. For example, some people had a headache, some people had the sore throat, some people had the runny nose, and based on the different symptoms, we can take a different medicine to treat them. Or so that's why if we are thinking about the process of the disease, it actually from the from infection of the single cell level. So if we can detect the symptoms of in the single cell level, it will help us to declare disease at any stage and prevent them at any as possible. So cell actually is a living system. For example, different nanoscale reactions happened inside the cell, and different transportation or different dynamics inside the cell happen in the cell simultaneously, just like the human body. The cell should also have some symptoms once they are infected by the virus or microvirus. So in our group, we are trying to understand the symptoms of the cell. For example, how does the pH and the radical and the chemical reaction and transportation or rotation, the temperature, this kind of symptoms change the inside the cell. And so later we can manipulate this kind of parameters, try to communicate with the cell, and help us also help us to have a better understanding in a single cell level. So today I will mainly focus on the detection the symptoms of a cell, such as the pH, and the radical, and the temperature. So since cell is in a micro scale size, so if we would like to detect the different parameters inside the cell, we need a specific meters. It should be sensitive enough and it should be small enough, which you can put inside the cell. So here we use the diamond, nanoscale diamond. As you know, diamond is composed of sp3 carbons. It provides us very it provides us very beautiful and very shining properties, such as work at the jewelry. However, if we introduce some defect, which is usually think is the bad things for the jewelry, it works as an impurity, but as a scientist, it actually provides us additional properties to use it as a meters to detect different parameters. So here, for example, if we introduce a nitrogen vacuum center in diamond lattice, the one nitrogen atom replace the one carbon atom, and then if we let the adjacent vacancy, it will form a nitrogen vacuum center, just like normal fluorophore. When the electron was excited from the ground state to the excited state, it comes back to the ground state with photon emission. That's why we have fluorescence. For the nano diamond, it works as the same. When the electron was excited, or excited from the MS0 orbiter in the ground state to the excited state, it comes back with photon emission as well. However, when the electron was excited from the MS plus minus 1 orbiter to the excited state, it comes back to a metal stable stage and come back to the MS0. This process is non-radiative. That means we don't have a photon emission in this process. So we actually have two states in the ground state of the nano diamond, the bright state and the dark state. The energy gap between the bright state and the dark state is in the microwave frequency range. We call it zero-phase splitting. If you think about we sweep the microwave frequency, at a certain microwave frequency, we will pump the electron from the bright state to the dark state. If we monitor the fluorescence, we will find at the certain microwave frequency 2.87 gigahertz at cell field. It will have a lowest fluorescence. By use of these properties, we can use it nano diamond at the thermometer. When the temperature increase, the diamond lattice will expand. So the cell field split energy will increase, and the resonant frequency will shift to the lower frequency. So by measuring the frequency shift, we can read out the nanoscale local temperature change. In addition, degenerated ±1 orbital will be split in external magnetic field to -1 and +1. Then what happened in the fluorescence spectrum? We will have two peaks appear. By measuring splitting microwave frequency, we can also read out the magnetic field. This is direct measurement of the temperature and magnetic field. But we can also measure the dynamics. For example, the radicals, it has unpaired electrons. The electron also have the spin, which will also produce a magnetic field. This magnetic field is alternating magnetic field. If we for our system if we try to measure it, we first pump the electron from 0 to ±1, and if we stop the microwave pump, the electron will automatically go back to the thermo-equilibrium state. In that case, we can measure the optical signal simultaneously to monitoring the spin state, either is in 0 or ±1, and we can find this relaxation time is usually in a few hundreds microsecond range. If we have additionally unpaired spins, for example radicals, it will resonate with the relaxation process and shorten the relaxation time. We call the T1 time. So with the increase of the concentration of the radicals, the T1 time will become shorter and shorter. So by measuring the changes of T1 time, we can quantify how much amount of radicals is around. So this technology is called optically detected magnetic resonance audio technique. So by using this technique, we first try to prove it can be used to detect the paramagnetic ions such as the iron-containing proteins, ferritin, and gadolinium ions. And we also try to detect some radicals in water. For example, we found the sub-10 nanometer nanodiamond, which had the distorted carbonyl group on surface and catalyzed the decomposition of the H2O2 to produce the OH radical as an intermediate. So by measuring the tiny magnetic field produced by the OH radicals, use the T1 relaximetry in 100 picomolar H2O2 solution, we can actually detect 2 or 3 H2O2 molecules. So later we try to move this system to a biological system. But the first issue we met is the poor colloidal stability of the produced nanodiamond. Nowadays, the conventional nanodiamond is produced by meaning of the HPHT, the high pressure high temperature microdiamond, and then we use the mixture acid to treat the surface to get the carboxylated nanodiamond, which could disperse in water. However, once we change it to a biological condition, it tends to aggregate. Once it aggregates, we are not able to bring them to the living system. So this is the first problems we met, and then we developed a technology called adsorption cross-linking strategy. We firstly adsorb the branched polyethylene, is a positive charged branched polymer on the negative charged nanodiamond surface with the resistance of polyvinyl pyridine as a stabilizer. And then we use the 4-ampere HS ester to cross-link the adsorbed polyethylene to form a network. After purification, we can get nanogel coated nano diamond. Later we characterize it with the FM in liquid mode. We can find all of the modified nano diamonds are single digital, and especially in the deformation mode, we can measure the thickness of the swollen nanogel shell because the diamond core is hard and the polymer shell is soft. They are around 10 nanometer. And later, we try to incubate our nano diamond to cell and understand how that the different ligands affect the intracellular free radicals. Here we select 3 representatives. The somatostatin is a membrane and targeting peptide. The TPP is a mitochondria targeting small molecules, and TAT is a nuclear targeting moieties, which are widely used for the drug delivery, or because when they try to use this simple or efficient ligands to deliver different particles to the specific locations. So, however, when they are evaluate the biocompatibility, most of the researchers focus on the cell viabilities. If they show the good cell viability, they think is biocompatible. So, but we try to look further. Even it doesn't kill the cell shows the good surviving, whether the intracellular parameters is still changing. So we first need to do the cytotoxicity to find the maximum safe concentration. Here is 100 micromolar, and then we measure the location to say where are our nanoparticles in. We found in the confocals they are we label the endolysosome with the lysotracker. We found most of them are escaped from the endolysosome inside the cell and go to the cytosol. And then we did the in-situ measurement in the living cell, try to add the different targeting ligands. We found for the somatostatin ST. Once we add the very low concentration somatostatin, we will say immediate drop of the T1 time that indicates the radical amount increase. And later we further increase the concentration of the somatostatin. It doesn't show the further increase, which indicates the saturation of the intracellular radicals in the cytosol. For the TPP, the mitochondria targeting moieties, it can bind it to the surface of mitochondria, which is well studied in the literature. However, we found it somehow inhibits the activities of mitochondria, which prevent the producing of the radicals from the mitochondria. Interestingly, for the TAT peptide, which is usually think it can penetrate the lipid bilayer of the cell. However, we found even it can block the lipid bilayer. It doesn't give additionally signal to the cell to produce more radicals in the cytosol. And later, one of my former master students who's tried to design a system at the beginning, at the past part, we are focused on the detection, but we besides the detection, we are thinking if it would be good, we can manipulate at the same time. So that's why we select the MTHPP photosynthesizer, which could produce the radicals and light irradiation, and the nano diamond pose at a relaxometry to detect out the radical system. So that means we will have a system which can detect but also manipulate. And at that time, she just did the direct conjugation of the MTHP to the surface of nanodiamond, you can see there are a lot of aggregations in the system, and it's hard to uptake to the cell, but we can still see some is uptake by the cells inside the cells. And then she did the in situ measurement. Once we switch on the light, we can definitely see there are much more radical are produced by the MTHPP. However, later she decided to move to EPFL for higher salary. So that's why we need to look for other people to continue for this project. And the other part is about the temperature sensing inside cells. We introduced the indocyanine green is FDA approved photothermal agent to the surface of nanodiamond nanogel, and then we suppose the indocyanine green would be under the IID radiation. It will produce local heat, and the nanodiamond worked as the local thermometer could detect out the temperature change. In collaboration with the Pereira from illogical group in Ulm, we did the in situ ODMR measurement at that time, and we found for the NDNG and the NDNG ICG with the IID radiation. For the NDNG ICG, it shows the locally more than 30-degree temperature increase. For the NDNG, since it doesn't have the ICG as a photothermal type, it shows a slight fluctuation. Later, we try to understand how does the local temperature change affect the viability. We found if we incubate the very low concentration with the cell, and after irradiation, the cell can still survive very well. We later further increased the concentration of the NDNG ICG. We found the cell was significantly killed, which indicate even for the local temperature increase up to 30 degrees, if the heat does not accumulate inside the cells, the cell can still survive very well. Just like the human beings, we usually live in 37 degrees. We will not survive in 100 degrees. However, when your fingers accidentally touch the 100-degree water, you are still surviving. Only your fingers is hurt by the high temperature. Where I think in cell is also show the similar characters. We further did the additional confocal image to see whether we do have a higher internalization of the materials. We found that even we increase the concentration from 10 to 100, the real uptake is only 5 times higher. So later, we try to understand how does the local temperature change affect the transportation or movement inside the cells. Usually, the movement of large particle can be categorized to 3 groups based on the mean square displacement analysis. Namely, confined diffusion in the MSD analysis when the alpha value is less than 1. The Brownian motion is a normal diffusion, and directed diffusion when the alpha value is more than 1, when this additional force existed. So we prepare a series of NDNG ICG complex with different ICG loadings. L means low ICG loading, H means high ICG loading. All of them show the good dispersity after modification, and then we can find they both are uptake inside the endosome system. And later we did the in situ ODMR measurement inside the found for the NDNG. It shows a scientific fluctuation. For the NDNG ICG-L, it shows around 20-degree temperature increase, and for the NDNG ICG-H, it shows more than 30 degrees change. And later, before we started how does the temperature change affect the movement of the vesicles, we first tried try to understand whether the chemical composition on the surface of the NDNG-ICG system will affect the movement, and then we're tracking the movement of the NDNG inside the cells. We found all of them show the confined diffusion, and it doesn't show the significant difference due to the different chemical composition inside on the surface. And later we did the in situ measurement before and after iodination. We found for the NDNG, it doesn't show, it still shows the confined diffusion because they are trapped in the endosome system. However, for the NDNG-ICGL and NDNG-ICGH, both of them show the transition from confined diffusion to a direct diffusion, which indicates the local heat actually could stimulate the cell to activate the active transport in the central transportation system inside the cell. And the last part, I would just briefly introduce you a recent topic we did for the pH sensing. Since you already know the nanodiamond could work at the reactometry to detect radicals at the faster part, at the less part, we coated the nanodiamond with the eomelanin pigment inside the cell, and then due to the free radical shift when the pH changes, so we can change the semi-colloidal radical amount inside the eomelanin layers, so that we can use it as the pH sensor to detect the different pH inside the cell. Here we did in a different buffer to see the T1 time. It shows the pH dependent. With the increase of the semi-colloidal radicals, the T1 time becomes shorter, and then we also found once we added in pH 7 ppb, and it takes around 2000 seconds to reach the equilibrium state. That means the reaction finished in 3000 seconds in the nanoscale. And later we used the cationic HSA as a transporter to bring them in the cell, and also additional measure the HSA coated nanodiamond to see whether it also shows the pH dependent T1 change. And then we found after we measured more than 20 different spots inside the cell, and found that the T1 time is around 77 microseconds, and which is actually located in 4.2 or 4.3 pH value. So this is further proved by the TEM. We can clearly see our RGS ND is located in the endosome, which is acidic condition. And the last slide, I would like to thank all of the collaborators and thanks Professor Tanja Weil. Give me the opportunity to lead small groups in department, and also would like to thank all of the group members in my subgroup, and thank you for your attention. Looking forward to your questions. Yeah.
Thanks for the nice talk from Dr. Wu. Are there questions from the audience? Yeah, I might have a question. So it's really nice to see your nanogel nanoparticle can go into the lysosome or different organelles, for instance, mitochondria, and also interesting to see you can create heats. So my question is whether you can create heats at organelle level. For instance, I can create heat to lysosome or this mitochondria. So perhaps in the molecular level, people always do like to see differences to see the heat shock. For instance, the heat shock is related to the autophagy somehow. And perhaps I see some correlations in between. Perhaps you can address more about this.
Yeah. This is a very good question. That is also the direction we are currently working on. So at the past project, we try to prove it can our concept can work, and now we are at more targeting moieties to the surface. If you go to if we go back to the better part for the temperature sensing part, we actually directly mix the indocyanine green with our nanogel system is absorption. So, but now we try to synthesize the large photosynthesizer which we can covalently bond to the surface, and additionally we can use the targeting moieties to modify the one side of the photothermal agent, and then the other side we can conjugate them both permanently to the nanodiamond nanogel system, later bring them to the subcellular organelles, for example, mitochondria. And then we try to understand how does the local temperature change affect the activity of the mitochondria. This is definitely what we are currently working on. I hope maybe in this years later we can have a manuscript sent out, at least at the preprint. Yeah. Thank you.
Yeah, thanks. Okay, if there are no more questions, I would like to thank Dr. Wu again. So I will introduce our next speaker, Dr. Xinjian Ji. Xinjian Ji got his PhD degree from Fudan University in 2020. He specialized in natural product biosynthesis and investigating catalytic mechanisms of the enzyme systems. After that, he joined the Professor Christine Hanna's group at the EPFL to do the postdoctoral research. He's now developing cyclized peptides for therapeutics. And today he will give us a talk about synthesized screening of the large library of the cyclized peptide for addressing the intracellular protein-protein interactions. And welcome.
Okay, thanks for your introduction, and it's my pleasure to join the webinar to show our research about the bioactive cyclopeptide discovery. So today my topic is about synthesis and screen large libraries of cyclopeptides for addressing intracellular protein-protein interaction. So the project goal it's to find the cyclopeptides against the challenging intracellular targets. To achieve the goal, our cyclopeptide should cross the membrane and then still have the binding affinity to the targets. And this target is normally some PPI. They will like the binding pocket or with a large the interaction surface. Normally, it's difficult for the classic small molecules. But why we will choose cyclopeptide for therapeutics? Because compared to small molecule and the antibiotics, the cyclopeptide still have the large binding surface to binding challenging targets. Also, the cyclopeptide has a constrained conformation, and when they bind to the targets, they will have a lower entropic penalty. So normally they will show higher affinity and selectivity. Also, some peptide is large, but they can have two conformations in this the water surface and the membrane surface. They will have a different conformation, and then in some conformation they will form the intraformular hydrogen bond to mask some polar surface, so they will show membrane permeability. With these properties, we choose cyclopeptide against these challenging targets. And in the last 20 years, some biology biological display methods show the ability to involve the cyclic peptide in the laboratory against some challenging disease targets. For example, the phage display to involve the cyclic peptide against some challenging targets, and they also find some very successful companies. Also, another very good technology, like we called MR display, they also could display some peptide against the targets, and then from the selection process, they will find the cyclic peptide to binding to the difficult disease targets. And also, they also find some very successful the companies. But the biology display methods have some limitation. Normally, this technology will display some large peptides and with more than 10 amino acids, so they will show low permeability. It's difficult if this peptide is not good for like challenging intracellular targets because they should cross the membrane. And also, this technology could generate small cyclic peptide, large the 6 members cyclic peptide. But if the 6 members cyclic peptide, normally they just have some million cyclic peptides. If only contains the 20 canonical amino acids, the chemical diversity is very low. So with this low chemical diversity, low number cyclic peptide library, it's difficult to fill the gap to exploring the cyclic peptides and then addressing the so-called undruggable targets. So, and another problem is the commercial available the microcyclic peptide is very small, and this limited numbers is not good for the challenging intracellular targets. So the question is how to efficiently generate a structurally diverse cyclic peptides library to exploring the potential to address the challenging intracellular targets. Our solution is to use the robotic combinatorial synthesis screen technology to access the cyclic peptide library. In the first step, we will use the commercial peptide synthesizer to assemble a short peptide on the 96 peptide to get the large numbers of short peptide. And because we use the SPPS, so we could easily incorporate the commercial available building blocks. This building blocks is a very large number, and then they will have the very good chemical diversity. And with this technology, we can synthesize the 384 short peptides in 3 days. And then this peptide will show the high quality. They can further for the next step usage without any purification. This number is quite good, but we think we also upgrade the commercial synthesizer. Now with the Hadwell upgrade, we can synthesize the peptide in the 384 well plates. With this upgrade, we can use the same time to get the 1536 cyclic peptides. This number is quite good, but for the challenging target, it's still limited. So in the next step, we will use a late stage diversification by nanoscale synthesis. Use ECHO to transfer the different precursor peptide in the density plate, and then use the robotics, coupling reaction. We can easily diversify the precursor peptide to get the very large number library compounds. With these compounds in hand, we can easily to screen these compounds against some targets with a multiplex screen assay. Normally, we will use the fluorescent-based assay, like TR-FRETES of PSA, to ranking the activity against some targets. If we want to explore more large library, we will also could incorporate the affinity selection and the mass spectrum technology to do the hit discovery. And this technology, everything's incorporated into the automatic robotic platform. So with this technology, we can synthesize like 100,000 compounds in 1 week with 1 person. So next, I will show some examples use this technology to screen some like PPI targets. First, we choose the MDM2 P53 interaction. This interaction is a very classic protein interaction, and also it's not very difficult because we could find in the binding surface they have some binding pocket, hydrophobic binding pocket, and with this hydrophobic binding pocket, we could have some information for the library design. So we designed the library based on the binding pocket. We fixed one building block with the hydrophobic side chain like phenylalanine and tryptophan, and another amino group we will use a backbone to introduce some stereo dimensions, the diversity, and also we will introduce the diamine acid. The diamine acid will coupled with the amino acid to give the more chemical diversity. So with this library, we use the FPSA to ranking the activity. The principle is like this: we will synthesize the binding peptide probe. If the probe binds to the targets, they will show high polarization signal. If our peptide inhibits the binding, the probe interaction, the probe will release from the targets, and then they will show low polarization values. With this principle, we can quickly access the synthesized library. We could find the some line. We will show the one acid. Will show the whole the dark green activity. This means that some artifact come from the acid, but also the peptide. Some peptide with the line like this one, they will come from the same precursor but with a different acid combination, and some acid combination show good activity. Based on this information, we synthesized the peptide and then use the direct FPSA to access the binding affinity. We find the peptide show the high nanomolar binding affinity, and then in the next step, because the library is our design synthesize, so we can easily to synthesize the small library with some building block analogs to exploring the structure activity relationship, also optimization the binding affinity. With this small library, some different the backbone analog and then diamine analog, and also some hydrophobic building block analog. We could find only the sequence with the original peptide showed activity, and also some new acid showed some good activity. Yeah, with this information, we do the next round of the optimization. Use several different the acid. We find we could easily get the peptide show the low nanomolar binding. So we in the proof concept targets, we accessed our platform. They should very successful example, and we could easily find the cyclopeptide against these targets. And now we move to some real targets and the keep-on nerve-2 interaction. This is the challenge target, but it's a valid target for inflammation and the neural degenerative disease, because it's role in mediating cellular antioxidant response. In this interaction, in a normal condition, the nerve2 will be ubiquitination and then degradation. But under the stress condition, nerve2 will release from the KEAP1, and then they will enter to the nuclear to introduce some oxidative stress response enzyme expression to protect the cell, to give a protection for the cell. And this target, why we say it's challenging target, because we can find this binding pocket. It's a slightly large binding pocket, and then the interaction is based on the charge interaction. It contains the 3 arginine conserved arginine in the binding pocket, and based on the normal design, we can easily use the native binding peptide to get the cyclic peptide. Quickly, we can find the peptide with the lower binding affinity, but this peptide contains 3 charge group. This group will prevent the peptide enter to the cell and to show the cellular activity. So, and if we use before we introduce the biology display method, we could find if we use the technology, we could find the peptide ligands that should a similar sequence of the native peptide. So it's with this peptide, we could difficult to develop the peptide choose across the membrane. But we want to find some good second peptide start point for the next optimization. So we designed the library. We use this format. We will fix one hydrophobic building block to introduce the aliphatic building block to introduce the hydrophobic interaction, and we will introduce a diamine acid for react with the acid to introduce the active to expand the library size and also introduce the chemical diversity. We also have the building block site with we will choose from the polar, backbone, aromatic, and aliphatic to try our best to introduce the chemical diversity. We synthesize the 1536 second peptide precursor and react with the 10 different acid, so we could easily get the 15,000 second peptide. With this peptide, we will use another assay we call the Tiafret assay. The Tiafret assay, the principle is like this. So we still use the fluorescent labeled probe. They were binding to the targets, and then we use the European labeled antibody to recognize the his target of the targets. If they form the complex, they will have the energy transfer to show the freight signal. But if our cyclic peptide disrupt the interaction, the Cy5 labeled probe will release from the targets. The complex will be description, and then the energy transfer will not happen, and then we will find the signal change. Based on this technology, we could easily access our thousands of compounds library, and then this assay will give us the lower background noise, and we could easily find the two hits. This hits will only has one carbon difference, but their activity will have a 10-fold different activity. And with this primary screen result, we quickly synthesize a small library to get the SR validation. We find the code structure. Based on the code structure, we synthesize another Fox library to optimize the affinity. Because we want our cyclic peptide can cross the membrane to active in the cell, in the intracellular. So we combine the activity and the membrane permeability, use the artificial membrane, lipid membrane to access the cell permeability. So we could easily find several hit compounds. We synthesize these hit compounds and then purify them to get the real IC50. We could find the several ones show the very good binding affinity. Most of them is in the lower binding affinity, and then we choose the two of them to get the co-crystal structure. We find their binding pocket, their binding site is in the native peptide binding locate, and then this peptide also show very good cell activity and then proteolytic stability. And then the continued development we coupled with the Swiss peptide development company, Obvious Medicine, for the next exploration. So, give us short summary. So we use the parallel synthesize with the commercial synthesizer to get a very large precursor peptide, and then use a high throughput nanoscale diversification to get a very large library, cyclic peptide library. With this large library in hands, we can easily to combine with different assay to access the compounds against the interest targets, and also the interest and valuable disease targets. Hopefully to find some ligands for further drug development. So thanks for your listening and also questions. Yeah.
Thanks for the talk. Other questions from the audience? Perhaps I have a questions. Really nice to see this powerful platform to have the diversity of cyclase peptides, and also really nice to see a lot of hits was found. I have a question like, do you have example, or are you also doing this for hit to lead strategies in this platform? You have found a lot of hits, but what about find leads? Do you have also diversity strategy, or you have very good strategy to have different moieties and develop the medicinal chemistry to find a good lead?
Normally, okay, so this technology normally it's good for hits discovery, because if we find some hits for some challenging targets, medical chemistry is easily to applied for optimize the molecule for next like leading compounds optimization. So, but sometimes the 0 to 1 is very difficult. Our technology normally provides the 0 to 1 start point for the next medical chemist for optimization.
But
also the some hits like keep on enough 2 hits. Now it's we can say now it's leading for the next the animal test something, but for the drug development still too long for us.
Too long. Yeah. So I'm asking whether you have a good strategy, or have you ever thought about your platform can also apply for the lead discovery?
Our goal is to find the hits, but probably we could also, because but what's so-called the hits? The leads. What's the definition? Normally, it's a leads for definition. So it's enter to the animal test, or what's the leads?
So to me, the leads
properties.
You are able to modify hits, different moiety structures that you have. You have a diversifier of your SAR, and then you find the best one, and you have provide several candidates to the further development.
So this platform could use for some properties of optimization, because like for example, we can easily find the binding affinity optimization, but for the membrane permeability, sometimes it's very difficult for the cyclic peptide. So optimization for the membrane permeability somehow it's very difficult. But our platform, because it could easily synthesize like 1,000 compounds, we can couple with we call it the artificial membrane or some kappa assay, cellular-based assay, to quickly optimization the membrane permeability. So based on which properties you want to optimize, we can develop some assay to perform.
Thanks. And second question is, now you are developing or using assays for the protein-protein interaction to disrupt the protein-protein interactions. And do you still also have assays to find a way to create a protein-protein interaction?
Create.
Like molecular.
Like molecular glue, right? But this is a very good question. This is my goal for the next steps, but in our lab we sometimes we find even if you find some molecule to disrupt the protein interaction is difficult. If you find some molecule to introduce the protein interaction, somehow probably it's like 10 times difficult than the protein interaction inhibitors somehow. But it's possible if you have a very good start point, like if you find some anchor could help to introduce 2 protein for interactions. Probably we could easily optimize based on this platform, but we probably need a very large library size, like 1 million something. But it's possible because the assay is the same. Now we find the signal decrease. If we find signal increase, somehow it's introduced the interaction.
Okay, thanks. And are there further questions from the audience?
Maybe I have a small question. Thank you very much for the live talk. So I just wondering, in the cyclization process, how efficient do you always use need to have the cysteine as a terminal amino acid, or could you explain a bit more?
So you mean how to generate the cyclic peptide? Which chemistry?
The cyclization. I assume you did the cyclization in the last step, right?
Probably no. Normally we have two strategies. So could you see this slide, right?
Yeah. I can see it.
So normally we will use this technology, like we develop some resin with the disulfide bond linkage, and then this peptide we can use the normal SPPS to get the peptide, and then we can use a TFA to remove the protecting group, but the disulfide bridge is still stable in the peptide, so we can easily wash the protection group, and then but the pure peptide is still attached to the resin. And then we have two technology. If we use the BDT to reductive release, we will get the two cell group. This cell group could easily react with the bioelectrophilic linkers to get the quite pure peptide. But
how efficient in
this it's very good. We soon we will have a review paper to access.
Because I'm also thinking, so you use the cross linker, you can also instead of cyclization, you also collect the two.
Polymerization. But in the lower because normally we would like to synthesize some short peptide, like 6-member or 5-member, and then we have some backbone building block inside. So and also the efficiency is quite good. Normally we will get in the slight lower condition, like the 1 millimolar condition or 0.5 millimolar cyclizing condition. Normally we will find the cyclic peptide, not polymerization. So very good.
Okay.
So the chemistry, but we have some different linker. We ranking like almost 100 linkers, and then we choose the 20 to 30. It's good, and then we use for library generation.
But how many amino acids? Yeah, how many amino acids you can add in your sequence and then make the cyclization? Is a limit?
This is random, but we would like to slight short because we still want to. The peptide has a membrane permeability to across the membrane to target the challenging intracellular targets. So normally we will not introduce too long peptide because the peptide bond is not good for the permeability. It's quite polar.
Okay. Okay.
Normally we want 5, 4, 6, 5. So we like this range. Yeah.
Okay. Yeah. Thank you. Many thanks.
Okay. Great. Thanks.
Good. Probably it's good.
Yeah, if there are no further questions, I would like to introduce Professor Liu Yuxuan. Just a second, I need to give him the. Yeah, okay, good. Yeah, Professor Liu Yuxuan was a INBO and Marie Curie Fellow in the Max Planck Institute of Biology of Aging in Cologne in Germany. And start from this year, he got professorship in the Southern University of Science and Technology in Shenzhen. And he will give us a talk about one of the mTOR inhibitor can prevent agents. And we're welcome, Professor Liu.
Thanks a lot, Professor Chen. Dr. Chen anyway, but you will be professor in some time soon. Yeah, it's my pleasure to be here. So let me just share my screen, my PowerPoint, and I hope everyone can just see my PowerPoint. Yeah. Good. Yeah, so if everyone can see my PowerPoint, I will just go forward directly. So first of all, I would like to just say that I'm now working in Shenzhen as a research professor. But this work, which I'm going to present today, is something that I've been working for many years in Germany. So that is one of the link that's why I will be here today. So as you can see on my title, I'm not going to repeat again, but basically we are going to talk about something that can make us live longer and healthier. So first of all, I would like to thank my postdoctoral supervisor, Linda Patches, and also my collaborator, Jennifer, Richard, and Irina about this work. And this is also supported by EMBO Fellow and YACI Advanced Grant. And actually, I'm also happy to make kind of a small announcement because maybe there's something we can collaborate in the future. So that despite that I moved back to China, I have kind of a spin-off screening platform in the Max Planck incubator called FlyScreen. So we are a team of 4, and we are now in a process to become an independent spin-off startup, biotech startup. Yeah, so today I'm going to talk about something more anti-aging. As you might know, that's if you look into the cosmetic industry, they always talk about anti-aging, make your skin looks younger, whatever. And scientifically, we would like to call it more like a geroprotection. So what is geroprotection? As you can see, we use strategies and interventions that aim to protecting against the aging process and promoting healthy health aging. Yeah, so first of all, well, maybe many of us we could ask, what can be considered as a good geroprotection? Yeah, there's 2 fundamental questions we need to address before we can answer these questions. So first of all, I think we need to ask, scientifically, why do we age? As we all know that most of animals, plants, actually most of the living organisms, they do age. So including human, that of course, that is something very conserved during the animal kingdoms. And nowadays, since many people working on the biological mechanism of aging, we can see that there's the latest version of hallmarks of aging. We now know that we have 12 hallmarks. So those hallmarks is something comes from the molecular, comes from the cellular, and also comes from systematic level. So it's something related to genome, related to epigenetic, protein, whatever. So most of the things you can consider that's linked to aging, yes, they are or hallmarks of aging. So that is the first question. But more importantly, if we want to develop a useful geroprotection, we need to ask the second questions. So what can we do? So basically, what we can develop for intervention for aging. So nowadays, if I would like to say this is something is still under the process compared to the hallmark of aging. So I'm going to just present one of the professor which I admired, who actually is called Max Planck. He was a very well-known professor in aging field in the United States, but now he's also jumped to the biotech field. So he become a CSO for moving the things forward. So I can tell you why he make this decision. But anyway, let's go back to the science he present. So he present that if you go into look into the animal model, so there are quite a lot of intervention, including calorie restriction, rapamycin, which I would like to talk about more in detail later, but also some gene therapy and so on. So there's quite a lot of things that can make at least mice live longer. But there are many things that still have some side effects, which I would like to address before, right? But today I'm going to mainly talk about the rapamycin. It's a TOS-C1 inhibitor. So it has been shown to slow aging in multiple organisms repeatedly. So that's the reason why we like to do this experiment, because it has been proved in many labs it works. And nowadays, what we are going to do, we're going to do to minimize the side effects. Because there's a huge gap if you consider the basic biology research and the clinical research. So in mice or in some small animals, we don't really care about the side effect. We only care about whether this treatment or this intervention works or not. It works, then well, fancy. Then we might have a chance to get into the Nature Science cell, right? This is a nice paper, a journal that have a high impact paper. But this is something actually we don't know whether that's cause a side effect. But the side effect is something that if we want to move this intervention into clinic, so basically apply to ourselves, we are more care about whether this intervention is safe or not. Efficiency or effective is important, but first we like to ask if this treatment is dangerous or not. So that is something we actually when I did my postdoc in Max Planck, we are focused on these things. So we try to maximize benefit without unwanted side effects. Yeah, so today I'm going to mainly present one of my story which published on Nature Aging in 2022. It's fascinating, as I hope everyone like it. But the main point is like we know that in the rapamycin, when we treat it very long, it extends the lifespan in multiple animal models, but it also causes a lot of side effects. And one of the way we trying to minimize the side effect, we're trying to narrow down the treatment window. So because we know if you use the drugs fewer, then you might have a less side effect. But of course, we might also lose some of the beneficial. So let's see if we look into the fly data, which is on the right-hand side. And we treat the fly with rapamycin. So the black one is the control, the positive control. We know that it would anyway extend the fly lifespan, as you can see from A to F. So it always extend the lifespan, the black solid line compared to the black dashed line. Extend the lifespan. And then when we minimize the treatment window, so from different time points, we found that some treatment, of course, they work less efficiency in terms of lifespan extension in flies. But there are some treatment, for instance, if you look into the figure E and figure F, you got very nice lifespan extension, similar or in the same level to the chronic treatment, but you actually use far less drugs compared to the chronic experiment. So that is something actually we want to find. And okay, so, but that is some fly, right? We always ask if we want to go to the human, we first need to we need to go through the mice. So then we try to immediately, when we got the fly data, immediately jump into the mice. And we found that we trying to set up a similar treatment, but with less group, because mice is expensive and our time also very expensive, right? So we did actually two treatments. One is the chronic control, as you can see, from 3 months to 12 months. And the other one, we treat them from 3 months to 6 months, and then we stop that. And then let's wait to the 12 months, so the mid-age mice. And in flies, we already know, despite that I didn't have time to show you today, but we know that this short-term rapamycin treatment has some long-term impact on the fly gut. So therefore, when we jump into the mice, we immediately took the small intestine sample and tried to detect if there's something conserved mechanism happening in mice. And yes, I can tell you that for the figure A and for the figure B, we saw that the MAN2B1 and also the lysozyme, the B62, so everything related to autophagy, it goes up in the rapamycin chronic treatment, but also in the rapamycin short-term treatment, even though the rapamycin drug already withdrawn 6 months before. So that means there's some long-term memory keep in the gut, in the mice, but also in the fly, as I showed you before. And that is very cool. But of course, we also want to say if there's other ways to surpass the negative effect of using rapamycin, right? Because shortening the time is one way, but there should be a lot of different ways we can do in terms of maximize the benefit and minimize the adverse effects. So then we go back to the hallmark of aging, as I showed you. There's a 12 hallmark of aging, and we believe there's something that those hallmarks, even though they are kind of not interconnected, here, but we believe that they are interconnected in some way. So that's the reason I got into another paper I published a few years ago, which is I find it's very cool. It's called Old Drugs, New Targets. So rapamycin, we know that is a hit the mTOR-C1, right? So it changed cellular metabolism. It sometimes also affect autophagy, as I told you previously. But we found that in this paper, we found that rapamycin can change the way of our DNA is stored. Yeah, so let's go through the papers. So we start with fly, as I told you, because fly, for the aging research, fly or C. elegans is are perfect model because they only live, I mean, 1 month to 3 months for the entire life. So for us, it's ideally experiment target. So we took the fly from the young one, so the day 10 fly, 30-day fly, and 50 fly from young to mid-age and old time point. We dissect them, I mean, to separate 3 or 4 different tissues. And then we check the epigenetic marker like the histone methylation, histone modification anyway. So we found it's very tricky, it's very interesting actually, but also very striking is that rapamycin increase histone protein levels and alter chromatin organization in the gut only. Yeah, so we can, as you can see in the figure A, if you can see that we use the DAP staining. So if you are a biologist, you know what the DAP stands for, right? You stain the nucleus, the DNA. And in general, if you look into the 10-day without rapamycin, so the very left-hand side, you found that it's just normal nucleus, nothing special, right? But when you use the rapamycin, you see the rapamycin plus, then you saw that, okay, the nucleus changed. It's from normal size or kind of things, and now it become a donut. So they have a hole in the middle. It's quite dramatically because I mean this thing is not only happening in day 10, but also happening in the day 40. So the mid-old age fly is also have the same thing. It's more importantly when we do the epistasis experiment. So we try to, because we believe that that is something caused by the histone, right? So we're trying to say, okay, if we cause histone, then if we overexpress the histone only in those gut cells, whether it will have a similar effect on the chromatin. So yeah, we use this 5966GS histone 3, histone 4, this driver to boost the histone 3 and 4 overexpression only in the gut cells. And we found, we saw that overexpress the histone will create a whole phenotype similar to the rapamycin did. And when we combine these 2 manipulations, so together we saw the same thing. We don't see an additive effect. That means histone and rapamycin, they go through the similar pathway. And of course, when we saw this A and B, we also do the heterochromatin staining. So we try to understand if the heterochromatin also change, because that's relatively easy to say that because the total chromatin organization change, heterochromatin also change if you look into the figure C. And yeah, so I mean, when we got this very interesting phenomenon, we were trying to ask the molecular mechanism behind that, right? So we did the iron-seq. We find there are quite a lot of genes change. I mean, when we did when we treat the rapamycin with flies. So at the end of the day, we found some interesting protein related to autophagy related genes. One protein we call the BCHS, which I'm going to talk about later, is called blue cheese. I like the name. I mean, one of the reasons why I picked this gene is because I like the name. Because I don't really like the taste of a blue cheese, but I think the name is very, very nice. And blue cheese actually is one of the very good target, because if you look into the figure B, we saw the blue cheese. So the histone methylations on the blue cheese gene body, they actually change when you affect the chromatin organization, like use the 5966 gene switch or use the rapamycin treatment. And you also see that when you do the manipulation of a histone only, you also boost the autophagy. So you make the autophagy activate in the gut. So everything seems much very sense, right? And when you activate the autophagy, use a histone or a blue cheese, you found that it has some improvement to the gut. So first of all, if you look in the figure A, so that is the cell junction staining. So cell junction is something similar to your skin or the facial skin, right? When you get old, you lose some kind of like a junction protein or whatever protein, so you have a wrinkle and so on. The gut have a similar pattern when it get old, and also they will be leaky, right? Because you have the gap in between. So when you use rapamycin, you see the junction protein has high expression. That means they are much younger. And when you overexpress the histone H3 and H4 only in the gut cells, you also get similar patterns. And that is only one. That's the first benefit, but not the only benefit, because if you look into Figure B, Figure C, and Figure D, you have a multiple improvement on the gut, including the stem cell activity, and C is the tumor formation, the D is the gut leakiness. So everything looks perfect on the gut. And then we ask, okay, if everything good on the gut, do they also have a systematic benefit to the whole organism, right? So we did the experiment on the Figure E. We saw that rapamycin extend the lifespan, which makes sense. And we saw that when we overexpress the histone H3 and H4 only in the gut, you actually not only benefit the gut, but also will extend the fly lifespan similar to the rapamycin treatment. That means if we only manipulate one type of cell type, you will actually have the systematic benefit to the whole body, which I think that's very key points with the kind of technical message in this slide. And yeah, so but then because we previously talked about that rapamycin, they have something side effect, right? Whether this histone H3 and H4 overexpression will have some less side effects compared to rapamycin. So we assess the fecundity. So because we previously know that for the Figure A, that if you use rapamycin, despite that you get the lifespan extension, but you basically lose all the ability to laying eggs in flies. And you can also consider in human, maybe you also kind of like a condom should stop you to having baby. So that is actually not a good drug to kind of the trade-off, right? And some people don't want to have that. But if you overexpress the histone of H3 and H4, you are not going to damper too much on the fecundity. So you still have kind of a decent fecundity. You can lay eggs for flies. Maybe in a human, you can also have a baby normally. So compared to rapamycin, it has a less side effect, at least on the fecundity side. Yeah, so so that's the good thing. But the bad thing, when we look back to the interventions, it seems can only benefit half of the population. Yeah, so that is the final story I would like to tell you, is sex matters. So that is also another paper published with Jennifer, so my long-term collaborator, and in December, so the late 2022, so also Nature Aging paper. So we found that because when we talk about histone, so the previous paper we mainly use females. So but then since I'm man, and then we all, of course we also want to ask whether men can also get a similar benefit as women, right? In flies, we did the experiment. We found that flies, their guts seems different between male and females. So male, we have generally we have a very high histone protein level compared to female. And when we treat the rapamycin in female, we know that the rapamycin can increase histone protein level in the gut. But in males, that's not the case, because it basically in the control condition, the histone protein level in male gut is already high. So when you use the rapamycin, you are not getting higher, because then the protein is already too much. And that is also the lead to the similar thing for the blue cheese and also for the gut autophagy. In males, when you use the rapamycin, you're not going to get higher or not getting further autophagy activation. So that is a lead to something we try to say that, okay, if we are not getting the higher autophagy activation in the gut in males, maybe we are not going to get some benefit from rapamycin. That is actually true. But we want to see if there's some other way that we can still let the male to get some benefit as female they get. So in flies, it's relatively simple, because if we want to ask this question, we only need to do some kind of genetic manipulation, right? So in flies, we try to manipulate the sex determination pathway in the gut cells, because previous paper we know that the gut cell play very important role in terms of histone protein level and also the lifespan and also health span. So we create a chimera, the sex chimera. So what that chimera means, if you look in the right hand side, so for the control, it's normal males, right? Every part of the male flies is male. So, but we also create something like the male outside is male, but the gut is a female. So it's a kind of like a feminized male. And we saw that when we look into the gut, we actually found that if we have the feminized, the feminized gut, then they respond to rapamycin. So so this is the things, and also the gut the gut autophagy level also responds to. Everything goes with the sex of the gut. So that's of course is making a lot of sense, right? So if the gut is a female, then they respond to rapamycin. If the gut is a male, they don't respond to rapamycin. But that is the only gut thing. And we want to ask whether the symptomatic level, so the whole animal can also respond to this. So if you look into the figure D, so that is the lifespan. So we're trying to assess the whole, the benefits from when we change the sex identity in the gut. So it's very cool that because I told you previously that the normal male, they don't respond to rapamycin. So you use rapamycin, you're not going to get the lifespan extension as female gut. But if we change the gut sex identity in the male, so you have a female gut in the male, you start to get some kind of the lifespan extension similar to the females. So that means your gut is very important to control your, lifespan extension or response to rapamycin. So that is the final working model for this paper. So if you look at the left-hand side, so that is mainly female things. So we found that rapamycin can inhibit mTOR. So that's what previously the people already report. We found that in the gut, they had the rapamycin can go through the histone epigenetic regulation and then activate the blue cheese, the BCHS, and then they will go back to the autophagy and then activate everything and then get the lifespan extensions. And in mouse, so the right-hand side, rapamycin, when they inhibit the mTOR, they still inhibit mTOR, but there's no response. That is because the histone level is already relatively high, and then we are not going to get higher, when you use rapamycin. So that's the reason that you're not going to see this additional benefit from rapamycin. So that is the male condition. But if we change the sex identity in the gut, we will let the male response to rapamycin, and in female we also see something kind of like also go with the male stuff. So at the end of the day, the gut cells matter in response to rapamycin, also to the lifespan extension. So that is the last slide, because I talked about a lot, and I'm looking forward to have discussion with you guys. So. But I think I can actually ask your question about which intervention would you consider will be safe, effective, and practical in human in the futures. Yeah, so that is also my WeChat QR code. If you are interested, you can ask my question now, or you can also add me as a friend later on. So yeah, thank you. I'm happy to take any kind of questions.
Yeah, really thanks for this interesting talk. Are there questions from the audience?
I can stop it.
That will interfere our immune system. Compare you extend the the autophagy, but somehow you are interfering the immune system as well.
Yeah. Okay, that's a very good question. So yeah, you're right. I think I can tell you that the rapamycin is FDA approved drug. So the first target they're hitting is the kind of immune suppressor, so suppress the tissue transplantations. And yeah, so I mean that's of course is making a lot of sense that rapamycins influence the immune system. So I can also tell you that one of my ongoing project now in mice, we saw rapamycin can also, I mean, not only focus not only hitting the autophagy but also hitting the immune response. So yeah, you're right. There's kind of like rapamycin is doing a lot of things. So autophagy is only one thing. And in the fly model, we saw that if you only manipulate or mimic the autophagy activation in the gut, you will get similar benefits as rapamycin does. So at least in this case, we can say that autophagy is sufficient for rapamycin, I mean, related lifespan extension or health span extension in the case. In human or in mice, that might be more complicated, I guess. But we haven't done any kind of like experiment to only activate the autophagy in mice. So, but there's quite some paper already mentioned that if you activate the autophagy, I mean, systematically, you will get lifespan extension. So, I mean, it works, but we don't know the link between those things. And yeah, and I think, I mean, I hope I answered part of your questions because that I think the immune system is very complicated, and I'm not going to make any, I mean, guessing or suggestion before we actually have solid data on it. Thank you.
Yes, there's going to be a lot of things to do. And there's also a question from this is a test, I think it's from our Xiang. So what is your thought on the rapamycin's effect on lifespan in cancer patients, essentially those who have mTOR signaling alertations? Do you observe any dose-dependent signal feedbacks loop?
Could you repeat the question again?
Yeah, the first question is, do you think their effect on lifespan in cancer patients?
Yeah, that's good questions. So I mean, in our hands, we always use the healthy fly or healthy mice because our main goal is trying to see if this can work on the healthy population. So basically, the people don't have significant disease. But I mean, I think that is a very good question. I mean, we haven't done that, but I know that some people done that on the cancer. I mean, knockout. I'm sorry, so not knockout. It's the cancer model mice. So they also see some benefit on the cancer model mice. And I mean, in our case, even though we use a normal healthy fly or mice, but the fly and the mice, especially the mice, I mean, when they get old, they naturally also accumulate a lot of tumors. So, I mean, so I think that what we saw that at least in some organ, rapamycin treatment in a certain dosage, it can suppress some cancer, I mean, formation. So it has some kind of mild effect. It's not very strong, I have to say. So it's not like the anti-cancer drugs, like the other drugs, because rapamycin is not a very well-known anti-cancer drug. So it has some benefit on cancer itself. But I think they're more, I mean, has benefit on the cellular metabolism, like the glucose, mitochondrial, and also immune function. So I think the metabolism and immune function, these two things are the most direct target from the rapamycin or benefit from rapamycin. Yeah. And that is also one thing I would like to go, sorry. That is also one thing why I would say that why we always see the sex difference in terms of rapamycin, because we know that the immune system is one of the biggest things between the sex. So male and female, they have a quite difference in terms of immune response. So that might be one of the reasons why you see the sex differences in response to rapamycin. Thank you.
Yeah, I think the second question was partially answered. The question was, do you observe any dose-dependent signal feedback on your experiment?
That's a very good question. Yeah. So we don't, because in our hand, I did a test different dose. I mean, we did. I mean, some people. I mean, so my team did some experiment like a different dose, and we do observe in terms of lifespan extension. So you will see that if you increase the dose of rapamycin, you get like a stronger lifespan extension. But when you over that, you also have some kind of detrimental effect. So that's a very common, like most of drugs, or even not drugs like intervention, right? Even nowadays we talk about the exercise, I mean, or dietary restriction. So in mice, you can do 20 to 40% dietary restriction. You get kind of like a lifespan extension in some mice genotype. But if you're going to drop down the dietary restriction to 16 or 18, you're going to directly kill the mice. So that's also for human right. I mean, everything is you can't. So I can say in Chinese it's called 过犹不及. But I think that's the main point.
Yeah.
Thank you.
Yeah. Okay. Thanks. So, are there further questions from the audience? Yeah. If not, I would like to thank Professor Liu again. So we learned a lot from the rapamycin again. It was a famous drug, but now the new chapter is opening now. Yeah, thanks again.
Yeah, bye.
Yeah, bye. Yeah, okay. So the last talk is from my side. So I will just share my screen. Yeah, and I hope you can see my screen now. Yeah, so today I'm going to talk about part of my PhD project, which is synthesis of aspartic proteases probe and their application for interaction identifications. Yesterday we have talked a lot about interactions, so me as well. Just first of introduction of myself, I got my master's degree from the Chinese Academy of Science. I studied medicinal chemistry. Then I moved to Germany in 2017 to study chemical biology, especially chemical proteomics. I will talk about later about this. And then in the end of this last year, I moved to Max Planck Institute for molecular physiologists to continue as a postdoc. And my talk will following 4 points over here. And first of all, the background. So why do we start? So as we know, people are different. Also, patients, of course, different. But in most of the case, patients are treated different patients are treated in the same way. So in that case, you will have effect, output, and no effect, and adverse effect. So this is what we don't want. And therefore, the precision medicine was proposed, I guess, was 20 years ago, which would use a biomarker to do the diagnosis. In that case, you will differentiate patients by the biomarkers. And with different biomarkers, we can develop different treatments. Therefore, we can achieve a much more efficient therapeutics. So based on that, this is just an example about, I need to move this. This is just an example about the biomarkers in the breast cancers. So for instance, here you see the ER and HER2, which are those very famous biomarkers for breast cancers. And they defined by different cell lines. You see, that means you have different type of breast cancers. And also there's an emergent biomarker called cathepsin D, which is located in the lysosome, which is a lysosome proteases, and was proposed as a pro-prognosis biomarkers. And mechanism D, how does cathepsin D work. It's mainly located in the lysosome, as you see here. I need the laser point. Yeah, in the lysosome, but for the development, first is a pre-form of cathepsin D, which is inactive. When they transfer to the lysosome, it can cleave itself and become active. And as you see, along the way, it becomes mature. There are different locations, and also it related with different mechanisms and diseases. And one of it is growth factor release, which is important for the new angiogenesis, as well as the extracellular matrix degradations, which is related with the mobility of the cells. And in this case, we need to monitoring the locations as well as activity of the cathepsin D to differentiate different type of patient, different type of patient or different type of diseases developed over there. And so the question remains is how can we monitoring the cathepsin D, especially which locations? And second question is how can we monitor the activity instead of the abundance? Because if you think about antibody approaches, you can find the locations as well as how much amount of cathepsin D, for instance, here, but it's hard to monitoring the activity in this case. So therefore, we propose chemical probe approaches, which target the aspartic proteases here is the cathepsin D. So how does this construction look like? So for instance, this is a chemical probe. It has a substrates over here for cathepsin D in this case, which will give us affinity. And then we put on a photophotonic affinity warheads. Afterwards, it will covalently cross-link a protein, which has interaction with the substrate here. And in between, we have a reporter here, could be a fluorophore or could be a bioorthogonal handle. Afterwards, we can do enrichments. So here examples to show diethylene and azides, benzophenols could be the photoaffinity warheads, and there are fluorophores, for instance, cyanide, and there are also azides or alkyne for bioorthogonal reactions afterwards. And with this probe, that will enable us to do the detections, and then we can label the cathepsin D, for instance, and do the microscopic experiment, see where it's a location, and we can also run the gel to do the quantifications. Also with mass spectrometry, we can profile at the proteomics level. So with this concept, we start with an inhibitor, which is called peptidin A. It is an inhibitor of cathepsin D and pepsin, carnosine, and so on at the nanomolar scale. And our idea is introduce a very small photoreactor group over here. After UV radiation, you see it would create simply carbon, and then this carbon will react with the proteins, which is close by. If you have a binding pocket, and the reaction will happen in the binding pocket and cross-link with the protein, and afterwards we're going to analyze where it is and how much amount. So with this idea, we introduce photo affinity moieties along the sequence of peptidin A to access a photo affinity probe, and we do a solid phase peptide synthesis afterwards. And this is, you can see the labeling at the pure protein level. We can label pepsin and carnosine very well. And you see also with a lower concentration, we can still see the detection over here. And also with a low amount of enzymes, we can also see the detection on the gels. And after that, we go for the cell labeling. We lyse different type of cell. They have different concentrate, have different expression level of cathepsin D. As you see, the MCF7 of the breast cancer cell line express the most amount of the cathepsin D, as well as the HT29 also expressed. And we also did competition experiments with the original peptidin A. We can compete the signal on the photo affinity labeling. And afterwards, we did in-cell incubations. We incubate the probe with the cell culture and also see the labeling, which give us information. This is a very good working probe, and we can go further to the further investigations. So with that, on the geos, you see different bands. We also want to know what are others proteins, and in this case. So we go further to do the proteomics analysis. So how does this work? According to our workflow, we incubate the cell lysate with our probe, and then with bioorthogonal chemistry, here is a click chemistry, click on a biotin, and we can enrich a biotin with streptavidin beads and do on-beads digestions, and we collect the peptide analyzed by mass spectrometry, and then we can see which protein is enriched by our probe. So this is just a quality control and shows the pull down works quite good and the reproducibility here looks nice. And from the proteomics experiment, you can see the volcano plot. We have two comparisons. First is a probe, and against the DMSO, we can see for sure this is cathepsin D was enriched, and there are also several others. And one of the S100 proteins also interests because this is immunology related, and I will talk about it afterwards. And we also have another control, which is competition experiment. We use a pepstatin A as a regional inhibitor to compete the labeling. And then we compare with our probe, and we can also see the enrichment of the cathepsin D and also several other proteins is enriched. And so from two comparisons, we can see the enrichment. For sure, this is our target, and we can have a very good labeling and enrichment of cathepsin Ds. And also, we see other proteins are also enriched. And interestingly, this 100 S100 protein was reported as a substrate of cathepsin D. And then we go back to think about our workflow. So it's like, if you know about immunoprecipitations, it's quite similar. We immobilize the labeled proteins, and perhaps their interacting proteins is co-purified in our workflow. So that's the reason why we can see the interacting protein in our enrichments. Also provide us information. For chemical proteomics, always you get a huge list, but it's hard to tell which protein is exactly your target. But in this case, we also see the interacting partner of the cathepsin Ds. Yeah, so with this information, we go further with deep learning algorithms. Here, our collaborator from Würzburg helping us to do the predictions. We have different scores from the deep learning by the sequencings. As you see, we got very high score of this P62, and this is also related to autophages, as we talk about a lot today. And so this is very interesting. And then we go further to validate whether they really have or could really be the substrate of cathepsin D. We incubate two pure proteins together and see the degradation along the time of incubations. And we also do a cellular experiment. Here we have starvation conditions. Here we can see the increasing of the P62. But if we can see the decreasing of the P62. But if we treat with pepstatin A, we can see the rescue of P62, which means this provide evidence that P62 could be one of the substrate of cathepsin Ds. And also, of course, there are some remaining questions, and we achieve to identify quite a candidates, quite amount of candidates to show there could be interaction or could be the targets of the cathepsin of the probe. But we would like to highlight here. For most of the case, people just pick up the hits from your proteomics results. Okay, this might be one of the target of your probe. But in our case, we also find there are interacting partners here. And also to answer this question, to identify an unbiased ID for the probe targets, we also propose a different strategies, which is to find the modified peptide over here. But due to the time of limit, I cannot give you more information this time. Perhaps I can tell you more next time. And here is take-home information. Here we would like to say a peptiding-like probe can enable the monitoring of the aspartic proteases here. And we would like to highlight the PPA or the PPI, which is a protein-protein interactions barrier in your PPA data. In this case, it's affinity-based profiling data. You can also dig out your data and find more protein-protein interactions. And the last one is our results suggest P62 is one of the substrate of cathepsin Ds. And also their future perspective. And in our case, we show the affinity probe, which introduced diethyl ring as a photoaffinity warhead, could be a good probe set for the aspartic proteases. And this can be further developed for different type of aspartic proteases for the further probe development. And also, our probe can use for the further drug screening, because cathepsin D and other aspartic proteases could be very potent drug targets. And with our probe, we can get the readout of the protein of the proteases, and you can screen in different drug candidates to find inhibitors. And our probe is also a tool for bioimaging. We can introduce a fluorophore, and with a microscopy, we can go further to see the diffusion of the autophagisome and so on. And with proteomics approach, we can identify the protein-protein interactions with our approach. And this is also, we can go further to develop the probe for. And with that, I would like to thank my supervisor, Stephen Wehrhaus, and Albert Zigman for supporting my PhD, and also the collaborators from Beard School, from Scripps Research, and also from KU Leuven. Thanks my lab, and also the founding bodies. And also thanks for the audience, and waiting for your questions.
I have a question. So
yes,
great talk. Yeah. So as we know, the proteomics technology is quite used for several research field. So based on your development, like your probe, what's the best advantage compared to others? So can you explain what, like, just very short explanation? It's specific scientific question or for
yes. So this technology is much more potent for the targeted deconvolutions. For instance, you are doing a phenotypic screenings for certain molecules, but you don't know where is the target of your molecule. And this strategy can help you to profile which could be the targets. And this photoaffinity-based probe is a strategy that you can deconvert the target of your molecule. And also, this is a reference probe. For instance, in your case, you have a peptide-like. This is a peptide with fluorophore, and the probe I developed is also the case that you can use a probe for the fluorescent. This is a FP fluorescent polarization assays and so on.
Okay, so yeah, the internet is not perfect for now, but
yeah,
I can understand what you say.
Yeah. It's not perfect. Yeah. Okay, if there are not further questions, so I would like to thank all the speakers, thank all the audience, and also wish you a happy new year. And yeah, we will see each other tomorrow for our environmental session, I think.